Welcome to Study Loop.
This is chapter 27, problem number 22. We have a cyclotron and we're asked to calculate the orbital radius of an alpha particle. So let's remember the magnetic force is QVB. That is going to be equal to the centripetal force mv squared over r. So from here, let's try and isolate the orbital radius because that's what's asked in the problem. So these are going to cancel. We're going to have r equals mv over qb. So here in the problem, we're given the kinetic energy rather than being given the speed. So let's get that information also. As we know, kinetic energy equals half of mv squared. And now let's isolate the speed out of this equation. Then the speed is going to be 2 times the kinetic energy divided by mass, the square root of it. Now let's plug this as speed in the radius equation. So then if you rewrite r, it's going to be equal to m over qv square root of 2 times the kinetic energy divided by the mass. So if we actually cancel out masses here, what we're going to have is 2 kinetic energy times mass divided by the magnitude of charge and magnitude of the magnetic field. So this is the formula for the orbital radius, if we know the kinetic energy and the mass and the charge and the magnetic field. Now we have two, we're going to apply this formula for a proton and for an alpha particle so that we can find the orbital radius of an alpha particle. Let's look at the differences between the two for a second. So for a proton, we have the charge of plus E, right? It's 1.6 times 10 to the negative 19 coulombs. And the mass for a proton, I'm going to call it m sub p, that is 1.67 times 10 to the negative 27 kilograms. If we do the same for an alpha particle, then we have twice the charge, and we almost have 4 times the mass, which is 6.64 times 10 to the negative 27 kilograms. Now, let's write the orbital radius equation for a proton. So r sub p then would be equal to 2 times the kinetic energy, which is given as 300 kiloelectron volts, times the mass of the proton divided by the charge of a proton. Let's write for charge of a proton, let's put only E, and then we have times B, right? This goes all the way. Okay, now let's calculate the orbital radius for an alpha particle. Then it would be 2 keV, that being the same kinetic energy given to us in the problem, times the mass of the alpha particle divided by twice the charge of a proton times the same magnetic field. Again, this information is given to us in the problem. The magnetic field is constant for both. Now, is the same for both. Now, let's take the ratio of the radius of an alpha particle to the ratio of the radius of a proton. When we do this, we have square root of 2 ke ma over 2eb times, we're taking the inverse of this side, so it's going to be E times B over square root of 2 ke times the mass of the proton, right? So these are going to cancel out. The kinetic energies are going to cancel out, but we still have the ratio of ma to mp in square root. So going on the next page, as we said, our A R over RP equals to 1/2, so MA over MP. From this equation, we were trying to calculate the orbital radius of an alpha particle. The radius of the proton is given to us. That's why we don't need to do any calculation regarding that. So this should be the general formula that will give us the value for the orbital radius of the alpha particle. So then let's plug everything in there. 0.16 meters, I converted to meters divided by half, square root of the mass of the alpha particle, 6.64 times 10 to the negative 27 kilograms divided by 1.67 times 10 to the power of negative 27. 27s are going to cancel out. So then we're going to get 0.1595 meters. And if we convert it to centimeters, it's 15.95 centimeters for the orbital radius of an alpha particle.